Good afternoon, and let me first thank the organizers. It's been lovely to be here. Let's get started. I think it's the third time today we have seen this beautiful plot that shows the spectrum of magnetic field fluctuations as a function of frequency. And in the previous two talks, we have been focusing on scales close to the proton intrinsic scales, kinetic scales. In this talk, I'm going to focus on the MHD range of scales. The other thing I wanted to add here is that this is the spectrum that you measure at 1 astronomical unit. And actually, so all of this bunch of fluctuations have evolved from close to the sun all the way there. And so there is another time scale here, which is the expansion rate, that needs to be part of the picture as well. And so one of the threads of this talk is exactly to highlight the role of the expansion of the solar wind on the evolution of fluctuations. Okay, now we have discussed at length that solar wind fluctuations display all the symptoms of a turbulent medium. How do these fluctuations actually look like at the MHD scales? And what I'm showing here are magnetic field measurement from Parker Solar Probe during its first orbit. You have three colors corresponding to the three components of the magnetic field. In blue, yellow, and red, and in black is the strength of the total magnetic field. So first of all, notice that, well, they're overlapped, okay, the three components, but I hope you can see and appreciate that the amplitude of these fluctuations is gigantic. So the delta B is of the order of the B node. Second, I want you to focus on the radial component of the magnetic field, the blue color. You can see that there is a baseline here in envelope, okay, and this corresponds, so the reason why you see this envelope is because the spacecraft is in its inbound phase, so approaching the sun, and then outbound phase, okay? And so if you fit this with the radial distance crossed by the spacecraft, you see that it matches perfectly textbook the radial distance to the -2, which is what you expect if you have a radial magnetic field in spherical geometry. Good. Now, on top of that, you see that there are these gigantic spikes, okay? And these are the switchbacks. So switchbacks are humongous galvanic fluctuations, and fluctuations are so big that the magnetic field falls back on itself, momentarily reversing the polarity, and then it goes back to its original position. That's why they're called switchbacks. And here on the left, I'm showing a close-up view of a canonical switchback. Okay, so the top here in black, you can see the radial component of the magnetic field that in the switch sign. Okay, and in red is the total magnetic field strength, and the fact that it remains remarkably constant is an interesting problem, but it's the topic of a different talk. And the corresponding signature of magnetic switchbacks is that of a radial jet. Okay, so the velocity is reported at the bottom plot here. And this is because, like I said, these are galvanic fluctuations, and so the magnetic field and the velocity field fluctuations are correlated in the sense of Galvan waves propagating away from the sun. Okay. However, switchbacks are not your textbook shear Galvan waves. These are complicated 3D objects. And they're quite coherent in many respects, and sometimes, as in this canonical example, they really look like wave packets. Nevertheless, these switchbacks are an intrinsic part of the, of the galvanic turbulent spectrum. And a way to see that is to look at the distribution of the deflections of fluctuations quantified by this parameter Z. And alpha here is the angle formed between the total magnetic field and the mean field, okay? So if Z is larger than 0.5, then you have a polarity reversal, okay? Now, as you can see, it's quite interesting to notice that indeed you have a continuous distribution of these deflections, which is another way of saying that the switchbacks are intrinsic part of this turbulence, okay? However, I'm going to make a case that switchbacks are an interesting object, a strange animal to study on their own. Okay, and there are indeed many important open questions regarding switchbacks. First and foremost, where do they come from? Okay, and this is important because they can help us to understand the very origin of the solar wind. So some groups have posited that switchbacks, in fact, are a byproduct of processes in the corona, such as interchange magnetic field reconnection. Okay. And so they relate the generation of switchbacks to the formation of the solar wind. And other groups instead have argued and also shown with simulations, in fact, that you can get switchbacks starting from a bath of galvanic fluctuations, and then you can have either velocity shears here that drag the magnetic field, and so that's how you can get switchbacks, or the expansion itself of the solar wind can drive the formation of these switchbacks. Think about, especially these are classified as in situ scenarios of formation of switchbacks. If you think about this, you see that there are not many ingredients that are required to form switchbacks, okay? So that it is, it's likely that switchbacks are not specific to the solar wind, but you can find them in, many other astrophysical environments. The other important question is, okay, once you formed them, how do they evolve? And answering this question is important to understand that if they can have any impact at all on the thermodynamic properties of the solar wind. Now, key to this discussion is the role of the inhomogeneity of the medium on the evolution of fluctuations. And so this is the starting point to study the evolution of fluctuations and turbulence in an inhomogeneous medium. Obviously, capital U and VA represent the flow speed and the advance speed, and Z plus and Z minus are these Elsasser variables that represent counter-propagating galvanic modes. So you can see that if the flow is inhomogeneous, you have reflection terms here. Okay, so that you have a Z minus that's coupled to a Z plus and vice versa. And this is very important because then, even if you start with a purely imbalanced state, so purely outward propagating waves, you have inhomogeneity, and you get reflected waves, which go back to feed the nonlinear term here. So this is, for example, fundamental for the so-called wave reflection-driven turbulence, which is an important part of so-called wave-driven wind models, okay? Now, besides the reflection, there are also other important terms that couple a given mode of fluctuation with gradients of the background, which I call the large-scale coupling terms. And these terms, in fact, introduce a slow radial variation of the amplitude of fluctuations, okay? And so this is actually a result that's known like for decades and decades, okay? And the reason is that when you have a wave propagating in a homogeneous flow, the wave do work, in fact, mechanical work on the medium, and therefore their energy is not conserved. What is conserved instead is the flux of the wave action, okay? This is a completely general theory, and when you apply that to Alfvén waves in the solar wind, what you get is that the amplitude square of magnetic field fluctuations should decay as the radial distance from the sun to the -3. Now, this is crucial because if these fluctuations obey theory, then the background magnetic field, let's say, is mostly radial. It decays as the radial distance to the -2. Then the relative amplitude increases with radial distance, okay? And so this is also the key argument, okay, to explain how expansion can drive these switchbacks. So the fluctuations actually obey this is called WKB approximation. And so we have looked at data by collecting measurements from three different missions to cover a wide range of radial distances. And then for a given time scale, we have calculated the amplitude square of fluctuations at a given time scale. and put them in this plot. Okay, so what we have here is delta b squared, so the amplitude square of fluctuations as a function of radial distance in units of astronomical units. And you have three panels here, one per component. Now, for this talk, what's important is the leftmost, which corresponds to the radial component of the fluctuations. And you have two sets of dots, okay? The circles correspond to the RMS of the energies, okay? If you consider all of the fluctuations, all inclusive, okay? So if you like, all of the deflection parameters. And the triangles above correspond to the same quantity calculated over the sparse set of switchbacks, okay? You can see that this is a nice, power law in radial distance that you can fit, and the coefficient, I call it alpha. And this alpha coefficient is reported on the right here as a function of the scale. And what's very nice is that at the largest scales, you have this coefficient that's basically -3. So that's good. So the largest scales fluctuations obey theory. Now, if we consider, however, the sparse set of switchbacks alone, we see that they decay with radial distance much faster. And this coefficient, radial coefficient here is -4 rather than -3. Okay, so the conclusion is twofold. One, yes, the bath of galvanic fluctuations can be precursors of switchbacks, and then the expansion can give them a kick to form switchbacks. And second, once you have formed switchbacks, you have this amplitude so large that some process, this is our speculation, that some processes must come into play to put a cap on the maximum relative amplitude that you can get. And this is important because these processes, whatever they are responsible for converting energy stored in the wave into other forms, such as internal energy. Now, different processes have been investigated observationally and also with simulations that can erode and disrupt the switchbacks. One is, for example, reconnection at their boundaries, although it's a quite rare process observed. Dispersion, like the effect of dispersive waves, can also contribute. But what I'm going to focus here is the effect of parametric decay on the switchback. Okay. So this movie here shows a result of one simulation, okay, and this is a homogeneous MHD simulation. The black lines represent the magnetic field lines, and the color code, and the colors here, density fluctuations. And so you can see that this kink that we have modeled here, it's quite stable. It can persist for a couple 100 Kelvin times, but sooner or later it gets disrupted by resonating with these density fluctuations. And this process is the parametric decay. One of the signatures is the exponential growth of density fluctuations, okay, as represented in this plot. These are the RMS of fluctuation of density fluctuations as a function of time, normalized to the Kelvin time of the kink. The reason why you have multiple curves here is because in this case you don't have a volume filling galvanic system, okay, but you have a localized wave packet, and so boundary conditions in this case, as well as the box size, affect significantly the growth rate, okay. I'm not going to go into the details in that, but that's why you have multiple curves. The bottom line here is that, yes, the switchbacks can persist for a long time, so it's also possible, in fact, that they can be generated also near the sun. We cannot exclude that, but sooner or later they are doomed to collapse, okay? And when they do that, we have estimated with this toy model the amount of internal energy per unit time that you can generate, which is more than sufficient to match what's estimated from the data. So this is a promising result. Now, in the very 5 minutes, actually, right? I decided to talk a little bit more about parametric instability because I believe that this is an important process that can take place also in other astrophysical environments. And basically, what is it? Whenever you have an Kelvin wave, it could be a monochromatic Kelvin wave, a broadband spectrum, or a wave packet. If the amplitude is large with respect to the background magnetic field, then the Abel wave is unstable, and it decays by resonating with an ion acoustic mode and a reflected galvanic mode. Okay, and so it's particularly appealing because first, it's another way to generate reflected modes. Okay, and so it can complement the inhomogeneity reflection business. And the second, by generating ion acoustic modes, it can also enhance heating. And so recently, people have been reevaluating the role of parametric instability very close to the sun, because it has been shown that it can in fact contribute to heat and to heat the plasma and push the formation of the solar wind. This process, in fact, is most effective as the lowest the plasma beta is. So close to the sun is a region that's more favorable to this process. Okay. What I'm showing here is just to show some nice movies. Is a 3D simulation of a process of decay of an initial broadband galvanic spectrum, and the color represents the density. Okay, so what you're looking at is the evolution of density fluctuations. And so what happens, in fact, when the wave decays is that you form a kind of steepened front and shocks. So if you are in an MHD kind of context, you form a shock, you have your dissipation, and that's how you heat. Okay. Now in a collisionless plasma, the story is different. Okay. And so what we wanted to do is to investigate more in detail how does the heating process takes place through this parametric decay when you are in a in a kinetic model. And so we've done peak simulations, okay, to investigate energy partition. Another important aspect is to understand how the energy stored in the wave gets distributed among species. We performed the energy balance analysis, and we assessed that about 40% of the initial pump wave goes into reflected wave, and then 50%, almost the rest, 50% of it goes into internal energy. And this is represented, in this plot where the top panel shows the, the variation of the energy stored in galvanic modes. Okay, so it includes kinetic energy and magnetic energy. The second panel represents the the kinetic energy in the field-aligned direction. Okay, and then we have the proton internal energy and the electron internal energy, all normalized to initial pump wave energy. And so, okay, you can see, for example, initially you see that there is an increase in the bulk kinetic energy parallel to the field. Okay, so this corresponds to the formation of ion acoustic mode, which are still kind of fluid-like. Okay, but then you see that there is this drop here, and this is when you start to have kinetic effects in a strict sense. So to understand what happens, how this internal energy actually increases and saturates, you have to take a look at dynamics in phase space. Okay, and so this is an example, okay, of this is a snapshot in time, okay, during the saturation process of the parametric decay, and these two plots represent the phase space of protons. On the x-axis, you have x position, okay, normalized to the ion inertial length, and then on the y-axis you have on the top the parallel velocity of particles and the perpendicular velocity at the bottom. Okay, and so what you're seeing here is really like a contour, okay, of the distribution function. Yes. So the way this process works kinetically is that once you form, so there are two things that contribute to heating. One is you form ion acoustic modes, as I discussed, okay? And then what they do is that they trap particles, okay? And then they start to do phase mixing, okay? And so once you have filamentation in phase space, okay, ideally you will have a collision operator that takes care of it. We don't have that yet, at least. But the numerical scheme takes care of it, essentially, okay? And that's what gives rise to heating proper. There is another contribution to the heating, okay? Well, let's say increase in temperature, which is the generation of beams. So parametric decay forms very easily beams. Now, this is just, you know, it's not really to be, I mean, it kind of masks, it looks like there is more increase in parallel temperature, but in fact, it's just a coherent beam. And I will leave you with my conclusion slides. Thank you very much.
Yeah, thank you. All right, we have some questions.
Okay.
Please go ahead.
Thanks, that's a nice talk. I just want to understand a little bit more about these switchbacks and how to think about them. Are there large populations of switchbacks of different sizes happening all the time? Or, you know, are there these like faster, small switchbacks and larger, slower switchbacks? Ah, I see.
Yeah, so in fact, they occur over all scales.
Ah, awesome, awesome.
Well, at least MHD, all the way to about, at least what I found, 10 the ion inertial length.
Okay, so Martin showed us in his talk this beautiful plot of the solar wind magnetic field curvature function, distribution function.
Curvature. Okay.
Yeah, curvature distribution function for the solar wind. Have people made any connections between these switchbacks, which are obviously events of extreme curvature, and the curvature distribution functions that are measured?
No. But people are interested now to understand the effect of these switchbacks on energetic particles, how they affect the transport and their scattering. So that's one thing. The other thing in which they've been used is to study high energy particles, okay? So we have data on their pitch angle, okay, distribution. So people have analyzed if there is any change in the pitch angle distribution of this high energy particle. And if yes, then that puts a constraint indirectly on the curvature.
I see. Thank you.
Yeah.
Philip? Oh, or Axel?
Yeah, colors correspond to ranges in radial distance, which are reported on the right. What?
Yeah. Okay, go ahead, Axel.
You defined in the beginning an alpha that was the angle, I believe, of the magnetic field orientation, the local one.
Sorry, what was that again? I'm sorry.
You had an alpha in the beginning of your talk that was describing the angle of the magnetic field.
Yeah.
And I was then hoping to see some distribution function as a function of alpha, but you didn't have that.
As a function of, you mean this plot is a function of alpha rather than z?
Yeah, but it's I see.
It's not my fault.
It's just transformed so that it's positive because it swings all the way to a negative value.
Yes, and so so what I was wondering is whether you can describe it as an isotropic plus a uniform distribution, or whether that's really not the case. And what is the distribution for this model that you showed, which has a single switchback?
The distribution of,
I mean, this is the distribution, and you have a model that you presented from a simulation. Would that produce?
You mean this?
Yeah, exactly.
Okay.
Would that produce comparable? How do they look like? You never did that?
If there is a distribution for that.
Yes.
Now this is like an analytic shape that
sure.
I gave.
But would it be?
This would be one point with one of those values, right? I mean, it's just an example of at some 90 degrees or something.
Yeah, it will be on the top. I mean, here in the tail.
Or there, yeah.
Okay.
Yeah. Okay, Elliot?
Is it possible to evaluate either from the data directly or from theory the role of switchbacks in overall heating? So you highlighted parametric decay, some of the energy goes directly into the how energetically important is this channel?
Yeah, no, that's a good question. So, well, so you can use the toy model, and then, you know, from the simulation, you can extrapolate the rate overall the whole process. You know, what's the heating rate? I don't want to call it heating rate. In MHD, we have adiabatic closure, so it's not really heating. But in fact, it increases the internal energy through compressive flux, adiabatic compressions. Now, we have to do it with the data. People have to do it with the data. So some people have estimated the turbulent heating rate, okay, applied to switchbacks, okay, and they find that the turbulent heating rate increases when you have switchbacks. However, you know, there is a problem, because when you calculate these quantities, you're relying on a model, and these models are problematic because these fluctuations are highly imbalanced. So these are basically like Alfvén waves, so that then the nonlinear term is quenched, highly quenched. So it's kind of problematic to do that.
Okay, thanks.
Okay, I have a question for you, a little bit speculative here. So you know, us in heliophysics, like, this is one star, and we sometimes in heliophysics forget that people care about there are other stars out there. I have to say about maybe the implications for this as a heating process for just general stellar coronae, rather than just our own personal corona.
Well, yeah, no, like I was trying to make the point is that there's nothing really specific here that, you know, to the solar wind itself, right? I don't know, maybe.
Sorry, it's a tough question to throw at you.
I mean, no, sure. I mean, you know, I don't know if someone tries to model stellar winds, but I mean, probably the same kind of processes are valid, I would say, in a wide range of conditions, also for exploding bubbles that I've seen the other day.
Yeah. Okay, so we have one last question.
Yeah.
So I love PDI, but when I talk to space physics folks, they often ask me, okay, how do you observe it from Parker Solar Probe? I'll now turn the question back to you. How would you pick that out of the data?
No, and okay. That's the problem. So the problem is that there's no way, like theory and simulations, to just tell you these Alfvén waves are supposed to decay. Problem is that we do not observe strong density fluctuations in the solar wind. So it's either because you know, kinetic effects just, you know, undergo kinetic damping, although it's kind of an easy shortcut answer. But most likely, this process is important closer to the sun. That's where you have the most favorable conditions, really, they should not escape from that. But we don't have direct measurements there yet. There are indirect, you know, like observations. There is a group, I believe in Columbia University working on that, and they claim that they see signatures through, you know, like, observations in specific wavelengths, signatures of density enhancement consistent with parametric decay.
Can you put up that plot from Noor's paper, the switchback, the velocity change? I want, for context here for everybody, I just want to mention something. So, you know, it probably really does have a big impact on heating of the material around the sun, because notice when you go into the switchback, the lower plot is the solar wind velocity, and it jumps by a factor of 2. That's a huge amount of extra energy in there. And these switchbacks, the reason why Parker Solar Probe people are very obsessed with them is because we really never saw them before we got inside the orbit of Mercury. So they disappear. By the time the solar wind gets out there, they've gone, which means all that extra energy has just become part of energy in the solar wind. It's either, you know, sort of slow down, but it's going to have a big effect on the actually amount of heating. So you know, if you've never heard of switchbacks or you've heard of them but have no idea what they're about, I mean, that's the reason why people care, is because there's actually a lot of energy that is hiding in them, and it's something we completely never really expected, well, except for one thing. Or there's one paper where they had seen little bits of this right around Mercury, but when we got closer, they got really big, and they're kind of a really, you know, first order obvious feature of the turbulence that's close to the sun. And again, it's probably a very general thing that we would see. So anyhow, that is the end. Please thank Anna once more.